I'm Todor from SoftwareAG. I work on the common runtime project, which is based on OSGi and provides the runtime for a number of our products. And I'm going to talk to you about a comparison of OSGi and Jigsaw, the Java modular system, from the point of view of application modularity. And I have quite a lot of slides and hope to squeeze them in 30-40 minutes, so I'm going to rush a bit. Hope this is okay. So the agenda is, first I'm going to define the use case which we're trying to solve, because I'm trying to make this really targeted rather than feature by feature comparison. Then I'm going to talk about how classes are linked, essentially, then how code is executed, generally in modular systems, go through JPMS and OSGi in terms of these requirements, and draw some conclusions and hopefully have some time for questions. So I tried really hard to be unbiased in this comparison because it's often the case that when somebody comes from a certain modular system, he's accused of bias given when such comparisons are done. So I tried to make a really abstract use case which doesn't have anything to do with modularity even, then try to define what a good module is, a reusable module, then draw my requirements from there rather than from any particular modular system. And then I evaluated the two modular systems which we have at present for Java from a generic perspective, essentially. And what's important is that for JPMS I use the best practices recommended by Oracle in their videos, for example, from Java 1. So, now our use case is this very generic thing that we want to compose applications from modules. And the important thing about these modules is that, first of all, they are in large numbers, so we need some automation there. They come from multiple projects, release streams I call them, and those streams are uncoordinated and independent. So you cannot force an open source project to rebuild their stuff because you break, right? You have to cope with that somehow and have a system which allows you to compose your stuff with theirs, or at least tell you when you can't. So this is what coordinated means. Everybody marches together, released at the same pace at the same moment in time. And uncoordinated, this is where we live, this is our world, nothing is released ever in the same time. How do we measure our success in this environment? So I think the very generic definition we can come from is a module's usefulness increases with the number of places where it can run. Right? And this is without requiring a rebuild due to the conditions which I described just now. So this definition basically means we measure the resilience to change of a certain module which is already built. And the change is, in the most basic sense, the difference between the compile time environment, like when we build what we see there, against the environment where we're forced to run. So can we cope? And further refining this, generally there are two types of resilience which I'm going to look at. The first is resilience to time. So can we cope with things that have changed since the time we built? And this is basically in two categories: functionality, the module we run against, added new stuff, so can we cope? And the other is refactoring, so that module retained all of its functionality but it was completely turned over inside. Maybe a project was redistributed between modules, so can we cope with that? And the other is resilience to scale. So when we add modules and grow the system, can we basically maintain our code? Does the system allow that? And there are two broad layers, as I described in the agenda, which deal with this. So both JPMS and OSGi can have finer-grained stuff in there, finer-grained layers. BJ talked about those. But I decided to split this into very broad categories. The first one is the module layer, which links stuff together. So it provides a consistent set of classes which can run. And this essentially the layer that handles time. So this is where all the version constraints should meet. All the classes should link without linkage errors. And then once this is done, you begin to execute. So there's something on top, I call it the runtime layer. This is the world of objects. And this handles scale, because this kind of dictates how you distribute your code. So the modular layer deals with time, and we measure time with versions in software. And under the conditions where we run, the important thing is that the things that run, the modules, really meet for the first time at runtime. So everybody was built against something else. Like in this case, in the middle we have some library. It was compiled against Log4j 2.0. We have some application later on in time. It was compiled against the library. And now our application reasonably wants to run against a newer Log4j. So really that library there will run against somebody from the future. So then the point is, can it cope? In this case it can. But in this case it cannot. Because Log4j has undergone a breaking change, right? The version was changed, the major version was changed. And now what can we do here? Really, we can't do much, but it's important that we know about this. So the modular system should allow us to tolerate changes to functionality for as long as possible, which is generally the second number, right, in a version, backwards compatible changes, and then no more, right? We should learn from the modular system somehow that we won't run and we will be precluded from running, so there's no errors of a random nature. And the other type of change which I talked about was refactoring. So these were changes in functionality, right? The version, the major and minor version change. And here it's about just restructuring. Your dependencies have restructured and you have to run against a new thing, but it still provides everything you need. So this is the build number at the end. So in theory, the best modular system possible will let you tolerate this forever. And the important thing which crops up over and over again is that your dependencies typically change IDs, right? Their names, because they're split, merged, renamed, moved around. Still things are the same, and their transitive dependencies change. So you should cope with that. Now, the other part, runtime layer, it's about distributing functionality between modules such that we can grow the system. And the best way we have found up to date to do this is decoupling, basically. And it always takes kind of this shape. We have an API which is stable. We have a consumer which consumes it. We have a provider which provides it. Both of them load the API. So this is their contract. And then somehow the consumer must get an object that implements this from the provider without depending on it, obviously, because otherwise the whole point of decoupling is lost. So both modular systems actually have this, and I'm trying to evaluate how good they do it. Now the abstraction they use is called a service, and this is not a particular class or something of this sort. It's really a communication mechanism they provide, which allows you to execute this exchange to get an object in 3 steps typically. So the provider must publish, advertise somehow that they have an implementation. The consumer must find it first, out of many implementations potentially, and then the consumer must bind, actually get an object. And the point is, the important point to notice is what happens after this exchange. Who actually owns the object? And what we typically have is, or at least the simplest case we have, is that the consumer owns the object. They get it, the control is transferred to them. But in this case, really, the complexity gets concentrated within the consumer. And we typically call that guy an application, and the providers are libraries, right? And basically, the application orchestrates everyone. It has all the power. It is convenient up until a point, right? At some point, adding more and more libraries becomes unsustainable to the application. Whereas the other way around, if the provider which gives you the object retains control, this actually ends up distributing complexity, because the provider actually manages the life cycle of this thing, the transitive dependencies, right, it requires of the object. Actually, it gives you typically just the business logic, right? The interface which a provider of this type gives you is pure business logic. There's no factories there, no configuration methods, no setters. It's all taken care of. And this is what's generally called a service, right? You just consume it, nothing else required of you. And this is actually the pattern you can see in dependency injection on a small scale. Right there, you're injected with a bunch of interfaces, typically by some third party, the dependency injection framework, and you just work with them. And this is how the classes remain simple. So what does Jigsaw do about these requirements? Well, first of all, I try to understand Jigsaw in the very broad terms of what philosophy drives its implementation. Right? There's something there underlying which is not just a hodgepodge of individual requirements. And basically, its simplicity, they state so themselves. And this, to me, after looking at it, boils down to first being minimal, which means that really it defines only the features you need to put, and only the isolation between modules, and it's familiar. Now, familiarity typically means you quickly transition to Java code, right? You express yourself in code as much as possible, and it uses familiar patterns like factories, for example. So its modular layer looks something like this. It has an artifact. It's, as many of you probably have seen, a jar which contains some other data, probably an optional main method. The metadata is binary, so we quickly transition to code. It's authored by humans, inevitably, because it's code, and maybe with compiler options. So pretty simple. This is how it looks for those who have not seen it. Right? This is a module of a certain name. It requires another module by name. It provides a service, so this is the second part, the service exchange mechanism. And this is basically it. Now, modules, what they provide really is not only Java packages, as we know, and they're versioned, but there is the caveat here that versions really, modules are versioned, but the versions really don't mean anything, right? That there is a valid JPMS version. So somebody else should know what this means and interpret it. And you can version a module by passing a compiler option, and it's highly recommended that you do so, in fact, I think by Oracle. Now what modules require, this is the other side of this layer, right? Modules provide, modules require, well, they require really an ID. This means that really the ID becomes part of your module's API. You're not tolerant easily to changes to this thing, so it's published for everyone. And really you can only add compile time dependencies. This is part of the simplicity, right? I have some examples there. You might need the framework at the bottom. You don't need its packages, you need the framework, like you need Spring. So, but if you declare this there, you actually need the packages. Or you may need an implementation of something. You know that thing there is an API. JPMS doesn't know that, and you need the implementation. But you cannot say this, express this in this module descriptor. You have to express this somewhere else, right, externally. And really, because versions have no assigned meaning, it's not easy to express things like, although I've seen 1, 2, 3, I cannot say I require up to 2.0, right? This is, again, has to be handled outside the scope of the module layer. So, what does this mean with respect to functional changes, right? Your dependencies change over time. How do you cope with that? Well, Oracle themselves say this is up to the build. So the build really must resolve a correct set of modules in terms of compile dependencies and runtime dependencies, so you can really execute an application. And it must also select compatible versions. And the runtime of JPMS really only checks the compile time dependencies and trusts your versions. And this is important to understand because they really say they resolve the dependencies, but they don't resolve anything because they preclude you from having any choice. Right? At that point, everything is set by the build. And this means that really the real metadata of your module is the build script, just like it's now, like it's today. This is by design the thing which really has to understand everything and resolve everybody. And also, as I said, we don't have an enforced version, so there's no universal way for two projects really to understand whether they're compatible or not. We intuitively trust the semantic versioning scheme, but it's good to have this really enforced mechanically by the modular system, just because it's not acceptable to have a linkage error, and we're trying to solve this issue. So with respect to, it's really, the things are as they are with respect to functionality changes. Now with respect to refactoring, the thing is that once you require somebody by ID, you get something called transitive fan-out, meaning you're not really tolerant to downstream dependencies or upstream dependencies changing, even if they're compatible. So since you publish your ID to the world, adding a module to your project is really a minor change. It's a new thing. Removing a module is a major change because somebody may depend on it. Even if the functionality is the same, JPMS allows you to offset this by having this request transitive, so that thing there is a facade now, and the thing behind the things behind it are refactored pieces, but really this adds two more IDs. So this is really another non-transparent change. So in this respect, really you have issues with this scheme. But it's workable. It's simple. So let's recap with respect to this layer. Really you are minimal, right? You have the module info, as I hope I demonstrated, only describes an isolation boundary. Like because it only has the compound dependencies, and they're supposed to be completely resolved. It only enforces that what you have discovered, right, that build time will stand. And it's familiar because you transition to Java code, and really you require things by ID, like most of us are used to from build system. Now the runtime there, that's the other half of the world, it is split in these three steps, publish, find, and bind. So what do we publish? We really publish a factory interface and a factory class. And the important part here is that you publish a class. It's a best practice by Oracle recommended not to publish the implementation of the interface itself. You should be publishing a factory, because somebody may iterate through all the implementations and to select the one they need, or maybe they just don't want to have resource consumption immediately when they see a service. So it must be really cheap to make the thing they get. So it must be some kind of proxy. They call it a proxy. It's a factory. And moving on to find, I hope you could follow. Again, it's a best practice for the factory to allow it to sift through all the implementations to get the thing you need. So it must have some type of informative method, which is again very cheap to call. For example, we have a hello service here, it has a hello factory, and the factory has two methods, get language and get format, and you can search for an English greeter that gives you JSON messages, for example, and get the thing you want. And finally, bind. How do you bind? Well, it's a factory. You call some method, we don't know what the method is, to get the actual object, which now can be expensive. And typically you have to control it, right? You have to configure it, do something else with it if you need to, and you own it. At least this is my understanding of a factory, which is the typical thing, right? Organizing something else is possible naturally, but it's not easy, and this is about what the modular system kind of drives you to do. So once you get the object, you obviously call it. And you can have a main method, which kind of concentrates, if you will, the flow flows from there, and the execution, all the setup goes from there. So again, does this high layer fit the philosophy? Well, I think it does. It does define only what you need to boot, which is a single main method. The broker which deals with mapping services providers to consumers, right? You have to have a service exchange mechanism guaranteed for by the module system, is just really an interface to class mapping, right? We know it's called service loader. It's available from Java 6. And this is familiar, obviously. We do everything in Java code, and we use a factory pattern. We publish a factory class, so it's pretty familiar, I think. Now, in summary, what all this means is really this is the model, I think, which JPMS advertises. It's familiar and simple, and we really have an application which is composed of libraries, and pretty much the JDK, which is the main use case here, is really a bunch of libraries. And although you have a lot of control and you start very simple, really, the issue here is that the concentrator of all the logic, the application, its complexity can grow unchecked. And what we eventually do is call that thing the dependency injection framework. We make it generic, and we pretty much go to a modular system next. I mean, to some, yeah. And the issue with that, so we have to evaluate how frameworks will cope with this, because really nobody will write eventually applications on the raw JPMS. You want your Spring running there, you want your CDI running there. Well, this means that given that we transition to Java code real quick, there is no framework neutral mechanism for frameworks to exchange these service objects. In practice, what happens is that a framework manages a set of modules in its own world, it accesses their internals and uses its own way to exchange objects between them. And I think this is what Spring does, for example. You have to really, in JPMS, open all of your packages to the Spring framework, not just the ones which are public. Let me see. And this kind of leads to a locking of frameworks, right? If that picture there shows that if I have a module written in CDI and I want to collaborate with a module written in JUice, it's no easy way to do this because there is no universal exchange mechanism, typically. So OSGi, what is the philosophy of OSGi? So it's a bit different, and trying to chew through what it does, I actually came up with, first of all, its composability. The primary thing is whether you can have two things already built and compose them in as many environments as possible, really, and do what's needed. And there's another system which resembles this, right? The internet somewhat. It uses simple textual protocols, say the HTTP headers. It uses the closed format type of protocol, right? The REST verbs are a very limited set, but it has open semantics, like the message type. So the way to exchange stuff is very strict, so everybody knows it. But what you exchange is open. So, and what it's mandated by a public contract typically, so everybody knows what we exchange by some type of ID, and that's like the MIME type registry. And things are self-contained, so like in REST, your message can be handled, proxied, and so on, because it has everything on board, more or less. So this kind of resembles what OSGi is built around. Probably it had to become this, I think. So what does this mean for the modular layer? Again, an OSGi bundle is really a jar. It has an optional start-stop hook, so every bundle can have a life cycle. As I said, the metadata is textual, so it's the jar manifest. And it's generated. It's not authored by humans directly, it's extracted from your code. Really, because it's textual, so it's not so easy to write, but this has major benefits. So this is how it looks. This is my code, right? I have a package with my hello service. I will annotate that and say I export this package with version so and so. And then this package has an interface, and I'll say this is an interface I provide out of my package. So the consumers of my service will get an object there, and this will guide them essentially that they should import me with this version range, right, up to the next major breakage. But as long as I'm backward compatible, 1.349, it's okay. So, and now I have to plug this. So JPMS uses kind of an identity dependency model. You describe things you need by name. There's another way, and actually it's intriguing that JPMS also has that, right? So requiring something by name is really like using the new operator to get your dependency, right? I need a Hello Factory, but I'm going to create this particular implementation which I know by name. And eventually we transitioned really to this other thing called capability, where we have to decouple things. And JPMS expresses this, for example, like that. So we provide something. Sorry for that. We provide an interface. This is the provider. The consumer says the consumer interface, as we know. And there is the broker in the middle, called the service loader. Now, if you try to express this pattern in a language-independent way, we can introduce some new terms. The interface could be called a namespace, right? It says what we want in some way. The provided thing can be called a capability. So this is the thing which really runs, which does the job. The user's thing could be called a requirement for that capability. And then generally, the broker in the middle could be called a resolver. So, and this is really in the core of OSGi, this decoupling pattern. And I hope from Java code, as an example, you understand why this is useful. So with that on board, what do modules provide in OSGi? Well, they provide capabilities. Capabilities have a namespace, like a package. They're expressed simply as a map, essentially, of predefined strings to values. There is a limited set of types, like I was talking about REST. You have string int and so on, and a very important type called version, which is special because it is semantic by definition. So the very data type is simply semantic. If you use it in your map, which describes your capability, this is what you're talking about. And now for packages, we have a shorthand way to express this. This is in the manifest of your bundle, the textual thing, and it says export package so-and-so version 123. This is equivalent exactly to that thing on top. There's a data structure inside of this type. Now, how do you express requirements in some language neutral way? Essentially, the point is to make this simple, language neutral, handleable, so tools can handle it, but still just powerful enough to do something meaningful. So requirements have a namespace. It's like requiring an interface of a certain type, and they simply have a filter, which is a Boolean expression over the capability properties. Like I can say I need a package named hello, its version must be more than 1.2, 1.3 must be less than 2. And again, for packages we have a shorthand way to express this, import package and a version range. This is again in the jar file. Now by the very nature of the version type, and this is all really that's needed, we have a meaningful compatibility check now. Because it's semantic, everybody understands what transition from 1.2 to 2 means. Now, the semantic type is really simple. It only has 3 numbers, so this restricts all projects which have all kind of funky names, typically legacy and whatnot, but they're restricted. Now they have a common contract, so independent parties can talk to each other. So this is the trade-off which we make to get more composability. And this is what we basically express with this import. We compile against 1.2, this is what we see, and we lock this information in that import up there. And this means that we're ready to accept future versions up until the breaking point. So this can be now verified by a mechanical process, which means it scales more. And the trade-off is you have to adapt to it, basically. Now, what does this mean about refactoring? Now, given that we don't have names anywhere, and we have this generic way to describe things, we can describe anything, more or less, provided we just defined our map of what a capability is. So, for example, we can say provide capability service there, and just list the interfaces which it implements. So this would be an analog of that service which I showed you. Or an extender. The extender is a name for a framework, right? I provide JPA, right? It doesn't matter which implementation I am, I provide JPA, version 1.1. And once you have this, the core of the OSGi framework, the resolver, which I talked about, the analog of the service loader on steroids, can use this data to purely symbolically and mechanically resolve all your links, more or less. So this is, once this is done, it doesn't know anything about JPA, for example. The code which later runs on top, when it started, simply introspects the metadata. Somebody knows I'm a JPA, somebody imported me, now I'm going to treat that guy like that they contain the entities, for example. And this is how you can make this pattern work and actually tolerate any refactoring, because as long as everything you declare there, which is exactly what you need in some sense, is there, you don't care how it's distributed between modules. So you can't get any more powerful than this without going on a class-by-class basis, which is not practical. As I said, the other side of the symbolic stuff, right? You can introduce then your requirements, which are Boolean expressions, right? So over a map of properties. So you can say on the second line there, I require JPA version more than 1.1. And a module which simply says their JPA and they don't say which implementation will be linked to me. And this is the gist of it, how it can be done. And there is a more interesting one, for example, I may require the native environment to be with such and such operating system, processor, language. These are simply extracted from the JVM, as we all know it can be done. But when they're made visible to everybody, you can actually be a bundle, a module which says I can only run on Windows. And this will be mechanically discovered, basically. I hope I'm not making it too complex. What does this mean really? So, for the general philosophy of the OSGi, it's textual, it's closed format, so they're just filters and maps. But what they mean, the implementations on top know. So you're open. And it's self-contained because every module really describes everything they need in terms of this type of thing. So this is how really the things BJ talked about operate. So for runtime layer, the same pattern holds, more or less. What we publish is an object and attributes, so a map. We sacrifice the generality of having a factory with informative methods of random nature, which somebody can introspect. We basically say to everybody, all you can describe your service by is a map, and that's it. But this instantly gives us the reverse side of the coin power for everyone to have a common thing to work against. And this is how it's done, really. When you need a runtime object rather than a service loader, there's a simple utility called a service tracker which can be used. And you tell it, I need an interface hello, and this is the thing I need. Right? This is the same Boolean expression, the same pattern calls here. And the interesting thing is that I don't need a factory anymore. I just get directly the business logic thing. Right? There's no hello factory anywhere visible, which means I don't have to manage it. Yeah, so the binding obviously is just to get the thing eventually pull it out of your loader and just use it. So you don't have configuration code there. Life cycle, this is important, how runtime state is distributed. Well, in the beginning I said that every module, rather than to have one global main method, every module has its own main method, which means they are able now to build their stuff and publish really objects, like, rather than have to publish classes. When you're in control of making your own stuff, you can set it all up and just publish the business logic rather than having to publish a factory. And this means an OSGi system is really a peer system. All modules are equal. You compose your modules, select a set that you want to get something, an application, and it emerges from the behavior of all the modules simply by virtue of them executing and doing their own thing. Okay, so what does this mean? Again, in terms of general philosophy, semi-textual protocols, almost textual as much as they can be. So as I said, all you can describe your service by is a map. You can require it with a Boolean expression. What this means, your interface that you get, what this means is open, so it's open again. Public contract, somebody defines their API, a project defines their API obviously, and it's self-contained because everybody have their own life cycle. So the summary for OSGi, I think objectively is this, right? Since all bundles are peers and manage their own stuff and they exchange objects which do the actual work, it's really an application being composed of simpler applications. Logically, when you work on a module in OSGi, you don't really care about anything external. You really care only about the interfaces which you consume, you compile against them, your own application. And then there's a second stage, really, right? When you compose modules, somebody consumes your modules, they select the thing you need. It might be you assemble your own application from the modules that you've built, and you run. So if you're your own application, it's a bit harder to implement a single module, right? But the trade-off is that you can grow easily because you really care about your immediate neighbors, so as things are added, you simply are not affected. What does this mean about frameworks? So now that there is a strict, simple, maybe too strict, I don't know, mechanism to exchange objects, frameworks can have generic code for that. And this means that frameworks really under OSGi look like this. You have your own framework running in every module, so say your own CDI container. And this then means that you are free to call to another module and you don't know whether they use a framework or not and what that is. And it's common to use multiple frameworks within an application in OSGi and actually even multiple JVM languages. So this is the trade-off of a slightly higher complexity, I think. So I'm trying to draw a conclusion here from all of this. So this is a table which I made for myself. Which are the really critical decisions which both of these modular systems took and what this led to, because they really do the job they set out to do, and you can't really argue against that. So OSGi wants composability, JPMS wants simplicity. Immediately, your modules are self-contained, the others are libraries. Composability, you have to have compatibility defined. If you want to compose random things, they have to know what they're talking about. So you have versions, you require capability, you require an identity on the other end, which is very simple and clean. For the runtime, similarly, there are objects on one hand, factories on the other, life cycles per module, life cycles the entire application. So they achieve what they set out to do. But where does this put us, right? We live in that world at the beginning where everybody is basically going to their own tune, and you have to cope with random change all the time to actually assemble a bunch of jars and have them work reliably. And the conclusion which I tried to make as objective as possible, I think, was that really OSGi is a bit of a better fit there. Because simply it's built on the same repeating pattern which we can see everywhere. Because the software industry doesn't seem to have invented anything better, right? It's the decoupling pattern of a clean API and then a provider and consumer working around that. In the module level, right, inside your code, we all know dependency injection. On the system level now, microservices are all the rage, but if you think about it, they have their own life cycle, their own state, clean business APIs, simple protocols like REST, so they can be grown and composed and changed. So it makes sense to have this in the middle, in the process level, right, in a single microservice level. And I call these services all the way down. So this is the meaning of that turtle's picture there. Everybody's kind of the same and nest within each other. And there's some resources which I hope I'll send the presentation, you can look at them. The interesting part is really in the middle, like what Alex Buckley, which is the JVM architect, says about the best practices in writing Java modules. And that's about it, and I really hope, let me see, I'm actually over time, but some questions? Anybody? Does it make sense? Very good. Not only to the OSGi people, right?
Thank you.
Thank you.